Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about how to model multiple discrete quantities within the same probabilistic model. This is going to be an overview because they're different moving parts, and I think it's very important that you see how they all fit together. So don't worry if you don't understand some of the details, there's going to be specific videos about each of them. Let's get to it. So we're going to discuss multiple discrete variables within the same probabilistic model, and this is going to be an overview. We're going to ask three key questions. First of all, how do you actually jointly model, how do you do this? How do you jointly model multiple uncertain quantities? And we're going to answer this question for discrete quantities in this video. Then we're going to ask, often we're interested in estimating causal relationship from data. Under what circumstances can we actually do this when we have a probabilistic model with several quantities? And finally, we're going to see that there's this thing called the curse of dimensionality, which makes it very challenging to jointly model a lot of quantities together, and how we can fight it. All right, so the first question is, how do we actually jointly model multiple uncertain quantities within the same probabilistic model? The way we do this is we represent them as random variables in the same probability space. Okay, so every time we deal with random variables, we have to deal with the fact that mathematically they're functions, which sounds really strange, but then when we actually use them, we don't really use them as functions. If you're a data scientist, you don't think of them as functions, you just think of them as variables that are described by probabilities. And we will see in a separate video how this is intimately connected, but let's review it very quickly now. We're going to do this through an example. So we're going to have a probability space, which is very simple, where we're just rolling two dice, okay? This is the outcome of the first roll, this is the outcome of the second roll, and together they're the outcome in the probability space. So the outcomes in this probability space are vectors which take value, each of whose entries take value in this set 1, 2, 3, 4, 5, 6, okay? So every time there's a die roll, we observe every time there's two die rolls, we observe 2, 3, 4, 5, 6, 1, and that's the outcome in our probability space. And now we want to jointly model multiple quantities associated to the die roll. What we do is we define functions of that outcome, which captures all of the randomness in this phenomenon that we're studying. So here we're going to define a function that represents the first roll, the second roll, and the sum of the rolls. And as you can see, they're just functions of this outcome, this two-dimensional outcome that I had defined. And the cool thing here is that this is going to allow us to capture interactions between these quantities. Why? Because the outcome fixes the values of all of these random variables at the same time. If the outcome is 3, 1, then the first random variable is equal to 3, the second one is equal to 1, and the third one is equal to 4 at the same time. So now we can talk about events such as the first and the third random variable are equal to 2 at the same time, or the first one is equal to 3 and the second one is equal to 1. We can also talk about conditional probabilities. What's the conditional probability of the first one being equal to 1 if the third one is equal to 4, and so on and so forth, thanks to this mathematical definition as functions within the same probability space. So even though this mathematical definition is a pain because it's kind of confusing the first time you see it, we should be grateful because it allows us to model interactions in a pretty elegant way. And it even allows us to model interactions when there's like an infinite number of random variables. We're not going to be looking at that, but just so you know, that's one of the main motivations to have this mathematical implementation of random variables. All right, so now let's take a look at how we describe those random variables. So what we're going to be interested in is in events of the form A is equal to a particular value and B is also equal to a particular value at the same time. So what am I showing you here? I'm showing you the sample space. This is the same sample space. And here I'm drawing all the points that map to A1 for a certain random variable A. Maybe I should have said that at the beginning. We have two random variables, A and B. And I want to show you how to jointly describe them using probabilities. And they're defined on this same sample space. So first we focus on A. These are the points that are mapped to A1 by this random variable A, and these are the points that are mapped by A2. We already saw in the video on discrete random variables that this is a partition. So, and also that by definition, if this is a valid discrete random variable, the probability of that guy and that guy have to be well defined. Well, if we're in the same probability space and B is also a valid random variable, then this event, which is all the points that map to B1, and this event of all the points that map to B2, they're also well defined. They have well defined probabilities. And in fact, in a probability space, if you have two events that have well defined probabilities, then their intersection also has a probability that is well defined. So if these two guys are discrete random variables within the same probability space, we can actually define these events, which is the event that A is equal to A1 and B is equal to B1 at the same time. And those are the probabilities that we're actually going to use to describe the joint behavior of two or more random variables in the form of the probability mass function, which tells you the probability that, for example, the random variable A is equal to A1 and the random variable B is equal to B1, or the probability that the random variable A is equal to A1 and the random variable B is equal to B2, which is this column in gray, which is equal to 1/3, which corresponds to 1/3 of the Venn diagram here. Okay, it's exactly the probability of this event, which is well defined because it's the intersection of this guy, and they're both well defined because these are valid random variables. Okay, again, more details about this in the specific video, but the point is that at some point we just forget about this completely. We don't even define it. We know it's there if you're a mathematician or if a mathematician comes to bug you, and you only work with this joint PMF that captures all the probabilities that we care about the two random variables, and this is the object that we end up estimating from data. This is the joint PMF. It's defined as the probability that the random variables take each of their possible values at the same time. Okay, this is the joint PMF. This is how we describe the joint behavior of two random variables. And again, I want to really emphasize this. This is what we actually estimate from data. We forget about the underlying probability space. We can do this for more than two random variables. We can do this for as many random variables as we want. Sometimes when we do it for a lot of random variables, we like to stack them as the entries of a vector, which we then call a random vector. And those entries are going to have a joint PMF, which is going to give us the probability that each of the entries equals a specific value at the same time. They all equal this specific, this vector of values at the same time. We can compute any probabilities describing the behavior of two random variables using their joint PMF. In this case, if we're interested in the probability that A is smaller than 2, so A is 1, and B is greater than 1, so 2 or 3, we just add up the corresponding probabilities, in this case 0.1 and 0.4, and we get that probability that we're interested in. So again, the joint PMF really captures everything you need to know about the joint behavior of these two random variables. What are the properties of joint PMFs? Well, they have to be non-negative because they're probabilities, and when you add over all of the possible values, because something has to happen, that sum has to be equal to 1. And in fact, if you have a function that is non-negative and satisfies these properties, then it is a valid joint PMF because you could potentially reverse engineer the probability space, although you're never going to do this. This is to say that when you're estimating a joint PMF from data, you just have to worry about whether it's non-negative and it adds up to 1 for it to be a mathematically valid joint PMF. Of course, that's not going to guarantee that the probabilities are actually the ones that they should be, but that's a problem of statistics, not of probability theory, if that makes sense. So this is just saying that from the mathematical point of view, as long as something is non-negative and adds up to 1, it's a valid joint PMF. How do we obtain a valid joint PMF from data? Well, it's important to realize that now we need joint observations of the two quantities that we're modeling. So here we're modeling these two quantities. We want the joint PMF at 2, 1. We need to see when the first variable is equal to 2 and the second one 1 at the same time, okay? And this happens 50% of the time here. So the probability here would be 1/2. And it's really as simple as that. This is how we estimate the joint PMF from data. We take the empirical probabilities. Remember that this is indicator variable that is equal to 1 if this condition holds. In this case, the data point, which is a vector, is equal exactly to this vector at which we're estimating the probability mass function, the joint PMF, okay, and to 0 otherwise. So essentially what we're saying is, what's the probability that the random vector that we're interested in is equal to the deterministic vector v. We see how many times that happens in the data set, and we divide by the number of data points. Okay, it's as simple as that. Let's see an example where we're trying to model precipitation in Oregon in 3 locations. All right, and what we say is that if it's raining or snowing at a location, then the value is 1 of the corresponding random variable. For example, here it would be there would be precipitation in Coos Bay, no precipitation in Corvallis, and precipitation in John Day. That happens for 30 of the data points. Okay, so here you see all of the possibilities. For example, for 7,253 of the data points, there's no precipitation anywhere. How do we compute a joint PMF out of this? We normalize. We divide by the total number of points. Boom, we have a valid joint PMF. Very simple. Often we want to isolate the behavior of individual variables. How do we do that? Well, here, if we're interested in only knowing what happens for A and we don't care about what happens for B, what we can do is we can aggregate. So for example, for the probability that A is equal to 1, we aggregate all the possible values of A equals 1, which means summing over B. Same thing for A equals 2, same thing for A equals 3. So we collapse that into what is called the marginal PMF that just gives us the probability that A is equal to 1, A is equal to 2, or A is equal to 3, and we achieve this by summing over all the possible values of B. For example, here we are only interested in what's happening in Coos Bay. For example, there's precipitation in Coos Bay. We have to sum all of the possible situations where it rains in Coos Bay. If we want to know the probability that it does not rain in Coos Bay, we have to sum all of those probabilities from the joint PMF. Okay, and that's what we get. That's the marginal PMF of precipitation in Coos Bay in this case. Now, a different issue is when we want to actually fix one of the random variables. Maybe it has been observed, or maybe we want to see what would happen in this hypothetical scenario where that variable in particular would be equal to 3. Then what happens here is that we're only in this part of the joint PMF. We know that this has not happened. So what do? We discard this and we normalize this to make it into a valid conditional, what we call a conditional PMF. So if we don't normalize, it's not valid. We need to normalize it to make it a valid conditional probability. We call that a conditional PMF. Realize that every time that we change this value, we're going to get a completely different conditional PMF over B. This gives us the chain rule. Okay, this formula here gives us the chain rule for discrete random variables, where the joint PMF is actually equal to the marginal times the conditional, and we can take it in any direction. And this also happens for many random variables. Essentially, this is very similar to when we had several events. First, you take the marginal over 1, then the marginal of the second one given the first one, then the conditional of the second one given the first one, then the conditional of the third one given the first one and the second one, and so on and so forth. And any order works, and it's critical to choose the order wisely, both in real-life probabilistic modeling, but also when you're doing homework. Okay, so here imagine that we know, well, we want to condition on it not raining in Corvallis and it not raining in John Day, which happens here and here. And here and here. Basically, that means that these probabilities are the relevant ones. So if we want to know the conditional probability that it does rain in Coos Bay given that, then we discard these guys and we renormalize these guys. That's going to give us the probability that it's raining in Coos Bay. But we have to renormalize by dividing by their sum. Okay, now we're going to compare the marginal that we have to the different conditionals, and they change actually quite a lot. So if it's raining in the other stations, it's much more likely to rain in Coos Bay. What happens when we compare a station in Hawaii and in Rhode Island? Well, here we compare the marginal of the precipitation in Hawaii with the conditions on whether it's not raining in Rhode Island or it's raining in Rhode Island. They're essentially the same. When this happens, we say that the two random variables are independent, which is not that surprising given where Hawaii is and where Rhode Island is. So we say that two random variables are independent if our uncertainty about one does not change when information about the other one is revealed. This is reflected in the conditional PMF, which is exactly the same as the marginal PMF, or equivalently by the chain rule, the joint PMF factorizes into a product of the two marginals. We can have independence for many random variables, and in that case we say that they're mutually independent if their whole joint PMF factorizes into a product of the marginals for all possible values of the random variables. Okay, so now let's go back to these three stations in Oregon. We're going to see that Coos Bay and John Day are not independent because you can see a pretty big difference between the marginal here and what happens when it rains in John Day. But now we're also going to condition on Corvallis. If we just condition on Corvallis, not raining, this is the conditional distribution of precipitation in Coos Bay. And now we're going to see what happens if you condition on Corvallis not raining and also John Day not raining. And what we see is that the difference is much smaller. Okay, so there is a slight difference here, but it's much smaller. Once we know Corvallis, the information about John Day is much less important to what is happening in Coos Bay. Similarly, if we condition on Corvallis being equal to 1, the conditional PMF of precipitation in Coos Bay is actually very different. But now if we incorporate John Day, here it does look a little bit different, but the difference is much less than when we don't know Corvallis. Let me go back to that. So this was when we don't know Corvallis, the difference is actually much more significant. If we take this to the extreme where once we condition, then the John Day would not change this at all, so these conditions would be exactly the same as this one. If that were to happen, then we would say that John Day and Coos Bay are conditionally independent given Corvallis. And given their geographic location, that's actually not so crazy, right? Because Corvallis is in between. If you know what's going on in between, then maybe it's less informative. It's definitely less informative what's going on in John Day. Taken to the extreme, there might be no information in John Day. This is not strictly the case here, but it's not such a bad description of what is going on. When taken to the extreme, we say that two random variables A and B are conditionally independent given C if our uncertainty about A does not change when B is revealed, as long as we know C. Okay, and this is captured by the the conditional PMFs. Realize that we always need to condition on C. All right, so now we go on to our second question. What if we want to estimate causal relationships from data? We can use conditional probabilities, but we have to be extremely careful. Let me give you an example. We have, and there's a video just about this, also about everything else, right? So again, I just want to reiterate, this is an overview. I know I'm going super fast. I just want you to see how all of these ideas are connected. So we have this example where we have NBA games from the 2014-2015 season. We look at 3-point percentage, and suddenly we see that Stephen Curry has a worse 3-point percentage than Courtney Lee. So if you know nothing about basketball, you would be, oh, I guess this Courtney Lee person shoots better than this Steph Curry person. And you couldn't be more wrong, right? Because Steph Curry is essentially the best shooter in the history of the game. And you can go to YouTube and look at some highlights. It's just insane how he shoots. So what is going on? Well, what is going on is that if we separate the shots between short threes and long threes, what we see is that short threes are basically threes that are easier because they're closer to the basket. Long threes are more difficult because they're farther from the basket. And what we see is that Curry shoots short threes better than Lee, and he also shoots long threes better than Lee. So he shoots better from close, better from far, but when we aggregate the data, and you can check that I'm not cheating, so just can check that if you sum these quantities, they add up to the totals. And then, very surprisingly, Lee seems the better shooter. So what is going on here? This is Simpson's paradox, where you are led to the complete opposite conclusion if you look at the aggregated data, but when you kind of separate it according to a certain additional factor, then you realize that the opposite conclusion is wrong. Is right, what I said there. But hopefully you got that, right? Okay, so the aggregated result is the opposite to what you see when you separate the data. So what is going on here? In order to analyze what is going on, we have to take a causal inference perspective where we have this observed outcome. If the shot goes in, then this observed outcome is 1, if not it's 0, and then we have a treatment T that tells us which of the players shoots. So typically in causal inference, this would be we put a vaccine or we put we give a drug to the patients. Here it is, does Lee or does Curry shoot? Because that's what we want to see, whether that has a causal effect on whether the shot goes in. Again, what we observe again is that, at least from the observed shots, it seems that Lee's shots go in. I mean, it is to Lee's shots go in more often than Curry's. In order to analyze this from a causal inference perspective, we define potential outcomes, which are these hypothetical random variables that tells us what would happen if Curry had shot every possible shot. Okay, is equal to 1 if they made the hypothetical shot, 0 if they didn't. Same for Lee. The potential outcome for Lee tells us what would happen if Lee had shot all of the shots, not only the ones that he actually took. All right, and what we actually observe is the potential outcome for Curry if Curry shoots, the potential outcome for Lee if Lee shoots. What we really want to know is if this potential outcome, if Lee shot all of the shots, would he make more shots than Curry if he shot all of the shots? What's the difficulty? We cannot actually observe this. When we look at our data, what we see is that when Curry shoots, in this case he missed, we actually see the potential outcome for Curry, but we don't see it for Lee because he didn't take that shot. Okay? Similarly for Lee, when Lee shoots, we see the observed outcome for Lee. Okay, it's the same as the observed outcome is the observed outcome if Lee shoots, obviously, but we don't know what happened with Curry. So we're missing what happens, whether Curry would have made Lee's shots, and we're missing whether Lee would have made Curry's shots. And those are called counterfactuals because they're counter to reality, because we cannot have access to them, because the shot was taken by the other player. But it's still important to model them if we're going to try to make a conclusion that is causal. So when is it true that what we observe, this is the percentage of shots made by Curry, percentage of shots made by Lee, when is it going to be equal to the actual probability that Curry would make shots or Lee would make shots if they shot all of the shots? Well, this only is true if the potential outcome is independent from the treatment, from the choice of who shoots. Okay? In that case, then this would be true. What would that mean? It would mean that the shots taken by Lee are very similar to the shots taken by Curry. This can be achieved, this independence can be achieved by just saying, okay, each shot is going to be shot randomly by Curry or Lee by flipping a coin with probability 1/2. This is what they do in randomized controlled trials when they're trying out vaccines or drugs. That is going to determine whether Lee is going to shoot or Curry is going to shoot. As a result, it's not that Curry is going to shoot more difficult shots or easier shots. They're going to be essentially the same because they're being assigned randomly to both players. If that happens, then we have independence and we can say that we know the probabilities of the potential outcomes. Okay, this is what happens in randomized controlled trials, for example, when they tried out the COVID-19 vaccine. This happens, so then we can trust those results. Are they independent here? Well, they're really not, right? Because Curry is taking many more long threes that are more difficult to make by both players, and Curry Lee is taking many more short threes that are easier to make by both players. So it's just basically that because Lee is taking easier shots, it looks like he shoots better, he makes more shots, but he's just making easier shots than Curry, who is taking very difficult shots. And there's other confounding factors, such as the fact that the other team is probably trying to hunt down, all of them are trying to hunt down Curry and avoid him from shooting, and that probably was less the case for Lee. Although I want to, definitely emphasize that currently was a fantastic player that has all my respect. So here, distance is a confounding factor that completely distorts the conditional probabilities and doesn't allow us to make a reasonable conclusion, causal conclusion based on the data. We need to correct for this confounding factor. In order to see how we can correct for this, you will have to look at the video on adjusting for confounding factors, or on the video, or at the video on Simpson's paradox. All right, so we have reached, that answered our second question. In order to introduce our third question, we have to first explain what the curse of dimensionality is. So remember that before, what we said is, oh, you want to capture the distribution of several random variables. Very easy. You just look at how many times they take their possible values at the same time. You normalize, boom. You have your joint PMF, you're happy, you can do your homework problem. What happens in real life? In real life, things like this happen. Like in the data set where I took those data from, there's 134 weather stations. So can I do the same thing? Can I say, let me model precipitation in these 134 weather stations in the US? So I just see what's the possibility that there's precipitation here, no precipitation here, precipitation here. I count them and I normalize. So how many possibilities are there? How many entries is this joint PMF going to have? So if you realize there's 134 stations, we have to account for the 2 options in each of the stations. So the possibilities are 2 to the 134. Imagine maybe this tree, if we have 134 stations, how many leaves the tree would have. We wouldn't be able to store the tree, if we had like all of Google's computing infrastructure. Like, it's just, this number is completely insane. Okay, the number of data that we actually have is 8,000. So it's just like a joke that we would be able to estimate these probabilities from data. Dependencies explode exponentially. And this is a very innocent example where we just have like around 130 stations, and each of them, have values that could be 1 or 0. So imagine if we have like thousands of variables, or if the variables are more complicated and can take several values. The joint PMF is something that we talk a lot about when we're doing probabilistic modeling for toy examples. In reality, the full joint PMF with all of the dependencies is completely impossible to estimate. You can completely forget about it. So now that's called the curse of dimensionality. When dimensionality goes up, which means that you have several variables, like many variables within your probabilistic model, forget about the joint PMF. Impossible completely to estimate it with the full dependencies. So how can we fight this? Well, the way we fight this is we make independence assumptions so that it is tractable to fit your probabilistic model. The joint PMF is simplified to the point where you can actually estimate it. And the model is still somewhat accurate. Very often you will make assumptions and you'll be like, well, but this is obviously, they don't hold, right? But then you have to remember that otherwise you might not even be able to fit your model. You wouldn't be able to do absolutely anything. So we have to live with some independence assumptions, even if they don't hold. Okay, so for example, in the precipitation dataset, we saw that Coos Bay and John were not really conditionally independent given Corvallis, but almost. So probably you just want to let that go and assume that and actually be able to fit a model, as opposed to not being able to fit a model if you have too many stations. So we're going to see 2 examples where we actually do this pragmatically to obtain a tractable model. The first one is in classification, where we have examples of data vectors that are d-dimensional, that are associated to some kind of class or label. So for example, you could think of the x's as pictures and the y's as what is in the picture, like dog or cat. That's kind of the classical example in machine learning. And the goal is, from a new picture, you want to say if it's a dog or a cat. From a new data point, you need to assign it its class. So a very reasonable way to model this probabilistically is to say, well, I'm going to model the data as a random vector x and the class as a random vector y. And now what am I going to do? When I get a new data vector x, I'm going to say, okay, what's the probability of the different classes given that particular value of x? And I'm going to choose the class that gives me the largest probability. This sounds amazing until you realize that when X is relatively high dimensional, and it doesn't even have to be that high dimensional, there's too many conditional PMFs, okay? Again, imagine that each entry in X can take two possible values. It has, like, let's say 100 entries, 2 to 100. This explodes. There are too many PMFs to keep track of. And this is, not that surprising because, basically this is the curse of dimensionality all over again that we just mentioned. So what can we do? We can incorporate independence or conditional independence assumptions. We're going to be looking in a separate video at naive Bayes, but essentially all of the machine learning deals with this issue where you have the curse of dimensionality and you have to make some simplifying assumptions to make it tractable to fit the joint distribution of the variables in your model. One such possibility, which is very simple but surprisingly effective for some problems, is naive Bayes, where you assume conditional independence given the class, even though that conditional independence does not hold, just to make the model tractable. The second example that we're going to look at is time series data, where we have that xi here is equal to a measurement at time I. Here I have, for example, precipitation at different times in a certain location, whether there's precipitation or not. A reasonable thing to do is to represent precipitation at each time by a random variable ai. So what happens if we try to estimate the joint PMF of ai to an, in this case where they can be either 0 or 1? Well, what happens is that the entries in the joint PMF again are 2 to the n. So unless you have a very ridiculously short time series, this is going to explode exponentially. It's going to be impossible to estimate this joint PMF. Again, we run into the curse of dimensionality. So what do? Well, we can assume independence, but if you assume independence in this problem, you're basically saying that all of these guys are independent from each other. You're not really modeling the time structure, which kind of defeats the purpose of actually modeling a time series. Instead, you can do the next most simple thing, which is making the Markov assumption that says that when you have a certain data point, if you look at its whole past, okay, it's actually conditionally independent of its past as long as you know what happened right before. Okay, that's the Markov property, surprisingly powerful, and it really simplifies the joint PMF. Why? Because if you look at the conditionals given the whole past, they just depend on the previous one. So when we look at the joint PMF and we apply the chain rule, okay, we just need to account for, so it's going to be the probability of the first one times the conditional probability of the second one given the first one. And here, usually, if we were trying to model all the dependencies, we would have the conditional probability of the third term given the second one and the first. But because of the Markov assumption, we only have one of them. And this massively simplifies the joint PMF to the point where we can estimate it tractably. An additional assumption that makes it possible to estimate this joint PMF, even if you have a single time series, is that you say that the transition probabilities are all the same, which again will often not be true, but it will give you a reasonable model that you can actually fit to the data. Okay, so for the precipitation data, you would compute the marginal probabilities to see what would be the probability at the beginning of precipitation or no precipitation, and then you would say the conditional probabilities of whether there's precipitation at one point given the previous point. You estimate them from data, and you say that there's this conditional independence assumption so that with just these two quantities, you can estimate the full joint PMF and do whatever you want with this probabilistic model of the time series. Okay. So what have we learned? We have learned how to jointly model multiple uncertain quantities. We define them as functions within the same probability space, but that's really just of mathematical interest. Really what we do is we define this object called the joint PMF that enables us to describe the joint behavior of the variables. Then we have to be very careful if we want to derive conclusions about causal effects from these probabilities that we estimate from data because of the presence of confounding factors. We should either randomize to ensure that the confounding factors are neutralized, or we should actually adjust explicitly for them if we cannot randomize. And then we also saw that surprisingly perhaps, once we actually try to jointly model a lot of, not even a lot, but a reasonable number of variables in practice, we're going to run into the curse of dimensionality, where joint PMFs are impossible to estimate in full generality unless you have a ridiculously small number of random variables. That's called the curse of dimensionality, and the way to fight it is to make independence or conditional independence assumptions that never really usually don't necessarily hold exactly, but that give you a model that is useful and allows you to do whatever you want to do while being tractable, right? While being simple enough that you can fit it from data. And that's all I got. Thank you very much.